Chapter 17 begins the concept that is often titled additional aspects to Equilibria. So we've had a basic Equilibria chapter where we talked about Kc and Kp. We then have started this next test with chapter 16, which is very specific to acid-base equilibria. There are two more major applications for equilibria in the solution, okay, so in the aqueous phase, and that is buffers for acids and bases, and then solubility equilibrium. Now, both of them revolve around what's known as the common ion effect. And what the common ion effect is, it's pretty much an application of Le Chatelier's principle. So we're going to have a system at equilibrium, and what we're going to do is we're going to disturb that system by adding what's known as a common ion. And that common ion will alter the equilibrium, which will then obviously have implications on the chemistry of the system that I'll explain here in just a bit. So if I look at the equilibrium reaction, which is an Arrhenius example because there is no water, of the nitrous acid, and we take a look at what happens, we do see that dissociates very weakly because this is a weak acid, and we get the nitrite ion here and the hydrogen ion here. So what the common ion effect means is if we were to add an additional source of a common ion meaning one of these two, and we will never add the hydrogen ion, so another acid, as a common ion. We're going to add this anion over here. So if we were to add another source of that, and in this bullet point here I talk about adding sodium nitrite, that will dissolve very readily, again, because this is a soluble a cation there. And think about what this does. According to Le Chatelier's principle, we have driven up the concentration of that product there, and this is going to want to shift to the left, thereby making nitrous acid an even weaker acid than before, because we're forcing more of this to go to the left due to Le Chatelier's principle. Now, a very common question is, what will happen to the pH of this solution when you add a common ion? Now, if we think about that, if we're going to force it to go back to the left, we're forcing these two things to bind back together. And remember, pH is dependent upon that ion being free in solution. So in this case, by adding a common ion, we make this an even weaker acid, thereby driving down the concentration of the hydrogen ion in solution. Now, another example of the common ion effect steps out of acid-base equilibrium and into solubility equilibrium. Later on in this chapter, we're going to explain why certain insoluble solids are actually said to dissolve a little bit. So what we have here is silver chloride, which up till now I've always said is a very insoluble salt, but it turns out that insoluble salts are still very, very, very slightly soluble, and we write the dissociation of those as an equilibrium expression. Now, the way the common ion effect applies to this is, once again, we can make this equilibrium shift by adding a common ion. So should we add some, let's say, silver nitrate, a soluble salt of silver, we are driving up the concentration of the aqueous silver ion, and it's going to force this reaction, to go to the left. Same deal, if we were to add sodium chloride, we're going to increase the concentration of the chloride ion and once again force this thing to go left. So basically, the main takeaway message of the common ion effect is by adding a substance that is in equilibrium, you can affect the equilibrium position of the substance using Le Chatelier's principle. And I can't think of an example off the top of my head that's going to move these to the right when we're talking about the common ion effect. Almost always in the common ion effect, we are going to shift these things to the left here to reform a reactant. Now, where this comes into play and what we'll spend a lot of time on for the first part of chapter 17 is with what's known as a buffer. And anytime we can get a solution that contains an acid and some of its conjugate base, or a base and some of its conjugate acid, we get a solution that is very good at resisting changes to pH, and that's what a buffer is. So a buffer solution is a solution that is going to resist changes to pH when you add just a little bit of a strong acid or a strong base to them. Our blood is a great example. I talked about in class how we want to have our blood stay between 7.2 and 7.4, but there's all kinds of things that can potentially cause our blood to fall out of that range. If it were not buffered, it would fall out of that range very often. So in our blood is what's known as the bicarbonate buffer, and it keeps our blood very specifically narrowed in on that pH of 7.2 to 7.4. Getting into probably one of the more challenging topics here of this test coming up. So we'll go through these in a logical manner, but understand that these do take some time to fully understand. So first of all, we want to talk about how a buffer is formed. What we'll usually do is we'll start with an acid, and since we talked about the bicarbonate buffer in our blood, if we want to think about starting a buffer with carbonic acid, we would start off with a solution of that. Now, normally that's going to go about an equilibrium scenario here, and it's going to form a very small amount of this and a very small amount of this. However, if we can bolster or increase the concentration of this conjugate base, say by adding a soluble salt of the bicarbonate ion like sodium bicarbonate, what we have is a solution that is high in concentration of an acid and high in terms of concentration of its conjugate base. And what this does then is this is able to resist changes in pH, and we're going to explain this here on the next slide. This resistance is generated, if I can copy down our buffer from the previous page. Oops. We get a buffer here from the previous page. So we've got a solution who's high in concentration of this acid and high in concentration of this base. If you were to add an additional source of a strong base, such as sodium hydroxide, well, this substance here in the buffer is going to be able to react with that. So what's going to happen is this is going to act as an acid. It's going to donate a hydrogen ion to make water, and it's going to form more of this conjugate base. Well, we haven't really affected the pH all that much by doing that because this acid in solution has neutralized this hydroxide ion to form water. Well, we know water doesn't affect the pH of anything, and all we've really done is made more conjugate base. On the other hand, if we were going to add a strong acid, let's say nitric acid, to this, what this will do is this will accept that hydrogen ion that the nitric acid is going to want to donate to solution, and we're going to make more of our conjugate base once again, or I'm sorry, our acid, and we have made a substance that again is not going to affect the pH all that much. So this is how a buffer works. Now, this can't happen forever. Obviously, we're going to get to a point where if we add so much base, we're going to run out of this. Or if we add so much acid, we're going to run out of this over here. So what we get into is what's known as the buffer capacity, and this is simply how much of a strong acid or a strong base can be added in order to still remain effective as a buffer. Eventually you're going to add too much and you're going to overload the buffer, and it is going to end up changing pH pretty dramatically. So we get an example here of when you're going to exceed the buffer capacity. We can read through both of those there. So the final few things that we're going to talk about today would be the reactions in these four scenarios here of strong acids and strong bases, or strong acids and weak bases. We're going to talk about what happens when our solutions of these following four types end up reacting. So if we look at first the reaction of a strong acid and a strong base, this is a very rare condition to see because there's not much chemistry going on here. This reaction goes to completion. We essentially make water and no equilibria is established. And since this is an equilibrium chapter, there's not much in the way of anything exciting going on here to really make note of, other than the idea of the fact that we're making basically water anytime we react a strong acid and a strong base, and it's so key to understand that we don't establish equilibrium. For the remainder of these, though, we are going to establish an equilibrium. So we have an example here of a strong acid reacting with a weak base, and what's going to happen here is when we do that, I want you to notice what we form on the right side. When we react a strong acid with a weak base, we end up forming a weakly acidic solution because we're forming this weak acid here. So what's key to understand is when we go from this bullet point to this bullet point, we are now going to invoke the equilibria of this weak acid. And what we see then is when we do this, we end up with a weakly acidic solution because we form this weak acid as a result. Now, I do want to mention, when we react these things, I'm talking about reacting these perfectly. 1 mole of strong acid with 1 mole of weak base. We're reacting these stoichiometrically. So obviously, if we're adding a strong acid to a weak base and we add so much strong acid, of course the pH is going to be way, way low. But I'm talking when you react these things perfectly, the equilibria that we get, this is going to end up being weakly acidic due to the fact that this is the only thing left in solution. So when we get a strong acid and a weak base, we are going to make a weakly acidic solution due to the formation of this weak acid. Now the opposite is true when we go strong base, weak acid. So here we have a strong base reacting with a weak acid, and what's going to form there is we get a weak base on this side. So once again, we're reacting 1 mole of this and 1 mole of this. They react perfectly. So really the only thing left in solution at this point is going to be water and sodium bicarbonate. Well, we have to remember then that sodium bicarbonate is a weak base. So what happens here at the end is we're going to take this bicarbonate, okay, which is also this guy right here after the net ionic equation, and this is going to react with the water in solution and form its equilibria, and we're going to get a weakly basic solution here as a result. So the key thing for all these reactions here is basically rationalizing through what's going to happen, and we've really got to get out of our minds the fact that any of this is left over. Remember, these have reacted perfectly. There is no reactants left over, so nothing from the original strong base and weak acid is left over. We have to purely concentrate on the products, and in the products we have a weak base and something that does not affect pH at all in the way of water. Our last slide today is going to be the reaction of a weak acid and a weak base, and it's a quick one because no reaction happens. Neither of those is strong enough to pull the hydrogen ion off of the other. So a weak base, let's go ahead and imagine that reacting with a weak acid, HA. The weak base is not strong enough to pull off this hydrogen ion, so whenever we mix a weak acid and a weak base, we get no reaction. So that's a good start here for the start of chapter 17. Obviously, we're going to talk a lot about this in class, so if you're not perfectly fine right now, that's okay, but just having the base of knowledge is definitely important.